Good morning. In this session, we will discuss Theodolite Survey. So, first we will see what a theodolite is and what are the different parts of a theodolite. The theodolite is the most precise instrument designed for the measurement of horizontal and vertical angles, and it has wide applicability in surveying, such as laying of horizontal angles, locating points on line, prolonging the survey lines, establishing grades, and to determine the difference in elevation, and also to set out curves. Theodolite may be classified as transit theodolite, non-transit theodolite. A transit theodolite, or simply transit, is the one in which the line of sight can be reversed by revolving the telescope through 180 degree in the vertical plane. Non-transit or plain theodolites or white theodolites, so they are the type in which the telescope cannot be transited. The transit is mainly used and non-transit has now become obsolete or outdated. Next, we will see the different parts of a transit theodolite. First important part is the telescope. So that is the integral part of a theodolite. And telescope is mounted on a spindle known as horizontal axis or Trunnion axis. The telescope may be internal focusing type or external focusing type. In most of the transits, internal focusing type analytic lens is used. Next is the vertical circle. It is the circular graduated arc which is attached to the Trunnion axis of the telescope. The graduated arc rotates with the telescope when the telescope is turned about the horizontal axis in the vertical plane. By using a vertical circle clamp and its corresponding slow motion or tangent screw, the telescope can be rotated in the vertical plane about the horizontal axis or about the Trunnion axis. The telescope can be set accurately at any desired position in the vertical plane using this vertical circle clamp and the slow motion screw or tangent screw. The circle can be graduated either continuously from 0 to 360 degree in the clockwise direction, or it is divided into 4 quadrants. In the type of theodolites which we use in our lab, we can find the vertical circle to be divided into 4 quadrants. So here you can see to the left of the telescope we have the vertical circle. Okay. Next part is the index frame or T frame or vernier frame. Index frame is a T-shaped frame consisting of a vertical leg called as clipping arm and a horizontal bar called as index arm. At the 2 extremities of the index arm are fitted 2 verniers to read the vertical circle. The index arm is centered on the Trunnion axis in front of the vertical circle and it remains fixed. When telescope is moved in the vertical plane, the vertical circle moves relative to the verniers, with the help of which the readings can be taken. For adjustments, the index arm can be rotated slightly with the help of a clip screw. Then there are also glass magnifiers. They are placed in front of each vernier to magnify the reading. Also, a long sensitive bubble tube, sometimes called as the altitude bubble, is placed on top of the index frame. So here you can see the telescope. To the left of the telescope there is a vertical circle, and near to the top of the vertical circle to the left you can see the altitude bubble, and also a mirror is placed or it is hinged to the altitude bubble, and you can see the reflection of the bubble on the mirror so that you can check whether the bubble is at the center or not while doing the leveling. Next part is the standards or A-frame. In this figure, you can clearly see the A-frame. The two standards resembling the letter A are mounted on the upper plate. So, upper plate means you have that horizontal circle. On top of the horizontal circle, you have the upper plate, and on top of the upper plate, this A-frame is mounted. The Trunnion axis of the telescope is supported on this A-shaped standards. The T-frame and the arm of the vertical circle clamp are also attached to the A-frame. Then you can see the leveling head. Leveling head usually consists of two parallel triangular plates. They are known as tri-bract plates. So the upper tri-bract, it has three arms. Three arms means three sides of the triangle. At each vertex of the triangle, it is provided a particular screw is provided, and that screw is called as the leveling screw. The lower tri-bract plate, that is also called as the trivet plate, or it is also called as foot plate. So it has a circular hole through which a plumb bob. So here you can clearly see that particular hook. Okay, at the end there is a hook. Okay, so through this hook the plumb bob can be suspended. So in some instruments 4 leveling screws are also there, but when we did experiment in the lab, actually this hook was missing. That's what I told you. There is actually a hook through which you can suspend the plumb bob. Then two spindles or axes or centers. The inner spindle, so this part is actually inside the theodolite. So you can only see these spindles when you draw the cross section of the theodolite. So this inner spindle or inner axis is solid and conical in shape, and it fits into the outer spindle. The outer spindle is hollow, and the inner spindle is also called as the upper axis since it carries the vernier or the upper plate. So always remember that the inner spindle carries the upper plate and the outer spindle carries the scale plate or the lower plate, and therefore the outer is called as the lower axis. Outer spindle is called as the lower axis. So always remember this. The inner is called as the upper axis and the outer is called as the lower or scale plate, or so it is also since it carries the lower plate or scale plate, it is called as the lower axis. Okay, both have a common axis and it forms the vertical axis of the instrument. Now lower plate or scale plate is attached to the outer spindle. Okay, an outer spindle, and this lower plate, it actually carries the horizontal circle. Then the lower plate carries a lower clamping screw, and corresponding tangent screw is also there. With the help of this tangent screw, the theodolite can be fixed accurately in any desired position. When the upper clamping screw is tightened, the lower plate is fixed to the upper tri-bract of the leveling head. So on turning the tangent screw, the lower plate can be rotated slightly. So always remember, when the upper clamp is tightened, the lower plate is fixed to the upper tri-bract. Okay, so whenever you clamp the upper, what happens when the upper is clamped? The reading gets locked. Okay, so whatever is the reading, that will not change if upper clamping screw is tightened. So always remember this point. When the upper clamping screw is tightened, the reading is locked. Then the size of theodolite is normally represented by the size of the scale plate, that is a 10 centimeter theodolite or 12 centimeter theodolite. So that means that the diameter of the lower plate or scale plate is equal to 10 centimeter or 12 centimeter accordingly. Next part is the upper plate or the vernier plate. It is attached to the inner spindle. It carries two verniers. So there are also magnifiers at the extremities diametrically opposite. The upper plate supports the standards. It carries an upper clamp screw and a corresponding tangent screw for the purpose of accurately fixing it to the lower plate. On clamping the upper and unclamping the lower, the instrument can rotate on the outer axis without any relative motion between the two plates. If the lower is clamped and the upper is unclamped, what will happen? Lower tight aanu, upper loose aanu. So what will happen? The reading can be changed. Okay. And if both the upper and lower are clamped, what will happen? If both the upper and lower are clamped, the instrument cannot rotate about the vertical axis. Next part is the plate levels. The upper plate carries two plate levels which are placed at right angles to each other. One of the plate level is kept parallel to the trunnion axis and the other one perpendicular to the trunnion axis. But the type of theodolite which we use in our lab, it has got only one plate level, and that is provided on top of the horizontal circle. Here you can see the horizontal circle, and on top of the horizontal circle there is a level tube, and that is called as the plate level. So the bubble of the plate level can be made to the center by using the leveling head. Then there is a tripod. You know that tripod, it has three solid or framed legs. At the lower end, the legs are provided with pointed steel shoes. The tripod head carries at its upper surface an external screw to which the foot plate of the leveling head can be screwed. Then plumb bob. A plumb bob is suspended from the hook fitted to the bottom of the inner axis to center the instrument exactly over the station mark. Then we have compass. Some theodolites are provided with a compass, and that can be either tubular type or a trough type. Next, some theodolites are also provided with a striding level, so that is not required. So these are the different parts of the theodolite. So here you can very clearly see the telescope, vertical circle, then vertical circle clamping screw, tangent screw. Altitude bubble cannot be seen as it is on the other side of the vertical circle. You can see the horizontal circle, then there is an optical plummet through which accurate centering can be done. Then A and B scales are there on the diametrically opposite positions of the horizontal circle. Then you have the plate level, leveling head, leveling screws, then upper clamping screw, tangent screw, lower clamping screw and tangent screw. So also this is another image of the vernier transit theodolite. Here the vertical circle is to the left of the observer. So this is called as the left face. Okay. So we have to do the readings in left face, right swing, and also in right face, left swing. Now we will see certain definitions. First one, the vertical axis. It is the axis about which the instrument can be rotated in a horizontal plane. This is the axis about which the lower and upper plates rotate. The horizontal axis. Horizontal or trunnion axis is the axis about which the telescope and the vertical circle rotate in vertical plane. The line of sight or line of collimation. It is the line passing through the intersection of the horizontal and vertical crosshairs and the optical center of the object glass and its continuation up to the object. The axis of level tube or axis of bubble tube. It's a straight line tangential to the longitudinal curve of the level tube at its center. The axis of level tube is horizontal when the bubble is at the center. Centering. That is the process of setting the theodolite exactly over the station mark. That is called as centering. Transiting. It is the process of turning the telescope in vertical plane through 180 degree about the trunnion axis. Since the line of sight is reversed, it is also called as plunging or reversing. Then swinging the telescope. It is the process of turning the telescope in horizontal plane. If the telescope is rotated in clockwise direction, it is called as right swing. If telescope is rotated in the anti-clockwise direction, it is known as left swing. Then left face. If the face of vertical circle is to the left of the observer, the observation of the horizontal or vertical angle is known as face left observation. If the face of the vertical circle is to the right of the observer, then the observation is known as right face observation. Then telescope normal. The telescope is said to be normal or direct when the face of the vertical circle is to the left and the bubble is up. So that is called as normal. Then inverted means the telescope is said to be inverted or reversed when the vertical circle is to the right side and the bubble is down. Then changing face. That term means it is an operation of bringing the face of the telescope from left to right and vice versa. Now we will see the different parts of a theodolite in detail. So here you can see.
Okay, today we will.
Here you can see a telescope, and the different parts are being shown in a clear manner. Okay, this is the telescope. It is mounted on the spindle called trunnion axis. It has two lenses, eyepiece and objective. The telescope is fitted with circular graduated arc, and that is called as vertical circle. The vertical circle rotates with the telescope and it is graduated from 0 to 360 in the clockwise direction for the measurement of vertical angle, or it may be divided into quadrants. By means of the vertical circle clamp and its corresponding slow motion screw, telescope can be set at any desired position. To read the vertical circle, two verniers are fitted at the extremities of the index arm. The index frame and the vertical circle are clamped to the standard, or it is also called as the A frame. It resembles the letter A. The trunnion axis of the telescope is also supported on the A frame. The two standards resemble the letter A and they are mounted on the upper plate. To level the theodolite, it is fitted with a leveling head. Leveling head consists of two parallel triangular plates called as the tri-brach plates. Two spindles, they have common axis which forms the axis of the instrument. The lower plate is called as the scale plate, or the diameter of the theodolite, or the theodolite is designated based on the diameter of the lower plate or the scale plate. So these are the important parts. Okay, then we will discuss how to take a reading using a theodolite, how to take the horizontal angle. So the rotating thing is called as the vernier. So we know that the horizontal circle is designated from 0 to 360 degree, and 1 degree is divided into 3 parts. So 1 degree is 60 minutes, so each part will be 20 minutes. Now this 20 minutes is represented on this vernier. So here you can see that the 0 of the vernier is coinciding at a point after 95 degree 40 minutes. So from the main scale you will get the value 9540. Then you will be observing the vernier, and at a point 9 minute then 20 second 40 seconds. So 9 minute 40 you got a coinciding division. So from the vernier the value is 9 minute 40 seconds. So you have to add these two and you will get it as 95 degree 49 minutes 40 seconds. So that is how you get the readings in a horizontal circle. Now how to calculate the least count? So here we know that the vernier, the total divisions, if you count you get 20. So 20 minutes, that is divided into 3. So 20 into 3 you get 60 divisions. So total there are 60 divisions. Okay. So what is the equation for least count? Least count is equal to the main scale least value of the main scale divided by the number of divisions on the vernier. That is the equation. So the least value on the main scale is 20 minutes and number of divisions on the vernier is 60. So 20 minutes divided by 60. So 1 minute is 60 seconds. So 20 into 60 divided by 60. So you will get it as 20 seconds. So that is the least count of the theodolite. Okay, so that is how we calculate the horizontal angle, or we read the horizontal angle of a theodolite. Hope it's clear. Each small division on the main scale represents 20 minutes. So after 95, the second division means it is 95 degree 40 minutes. Now then you have to read the vernier. You have to obtain a particular point on the vernier which is exactly coinciding with the main scale. So here you got it as 9 minute 40 seconds. So that is the second value after second division. Okay, so that is 20 second and 40 second. Okay, that is how you get the value. I hope it's clear. Okay, next we will see the different temporary adjustments of a theodolite. The temporary adjustments includes setting up, leveling and elimination of parallax. So this we have already discussed. So setting up means the operation of setting up includes centering of the instrument over a station mark by using a plumb bob or optical plummet. Then approximate leveling with the help of the tripod legs. And then leveling up means after having centered and approximately leveled, then the accurate leveling is done with the help of foot screws and with reference to the plate level. So the purpose of the leveling is to make the vertical axis truly vertical. So first you have to place the bubble tube parallel to any of the one side of the leveling triangular leveling head, and then use your thumb and rotate the screws either clockwise or anti-clockwise simultaneously until the bubble is at the center. Then turn the telescope through 90 degrees so that the telescope is now on the third foot screw. Now adjust the third foot screw slowly such that the bubble is at the center. Repeat the procedure in the same quadrant 2-3 times until the bubble is at the center throughout the run. So that is the procedure. Then elimination of parallax by focusing the eyepiece and focusing the objective. To focus the eyepiece, first you have to hold a white paper in front of the objective and move the eyepiece in or out until the crosshairs are seen sharp and distinct, and then focusing the objective. The telescope should be directed towards the object, okay, or a far away point, and turn the focusing screw. So focusing screw is the this screw which you see here. So turn the focusing screw until the image appears clear and sharp. So that is the procedure. Then measurement of horizontal angle. So next here you can see the instrument is centered and leveled over a point A, and you have 2 points B and C. So at B a particular ranging rod is kept, and at C also another ranging rod is kept. You have to find out the distance between the points B and C. So this is the first experiment. Okay, some of you have done this, but this class aims at revising the procedures for all of you. So okay, so at B a ranging rod is kept, and at C also a ranging rod is kept. So first we'll set up the instrument at A, then change the instrument to left face, okay, and set 0 degree at the A vernier in the horizontal circle. Then clamp the upper and loosen the lower clamping screw. Direct the telescope to sight the ranging rod at the leftmost point, that is B in this case. Sight or bisect the ranging rod at B exactly. Clamp the lower clamping screw. To accurately bisect the point, you can use the tangent screw corresponding to the lower clamping screw. So the tangent screw will work only after the corresponding main clamping screw is clamped tightly. അപ്പോൾ നമ്മൾ ബീനെ സൈറ്റ് ചെയ്ത് ബിയുടെ അവിടുത്തെ ആ ഒരു ലോവർ ക്ലാമ്പിംഗ് സ്ക്രൂ ടൈറ്റ് ചെയ്ത് കഴിഞ്ഞിട്ട് ഫൈൻ അഡ്ജസ്റ്റ്മെൻറ്റിന് വേണ്ടി ബിയുടെ ബി പോയിൻറ്റിനെ സൈറ്റ് ചെയ്യുന്ന സ്ഥലത്തുള്ള ലോവറിൻ്റെ ടാൻജൻറ്റ് സ്ക്രൂ യൂസ് ചെയ്യാം. അപ്പോൾ എക്സാക്ട്ലി ചെറിയൊരു വാല്യൂവിൽ, അതായത് മിനിറ്റ്സിലോ സെക്കൻഡ്സിലോ ഒക്കെ വേരിയേഷൻ വരുത്താനായിട്ടാണ്, കുറച്ച് അങ്ങോട്ടും ഇങ്ങോട്ടോ നീക്കാനായിട്ടാണ് ഈ ഒരു ലോവർ ടാൻജൻറ്റ് സ്ക്രൂ യൂസ് ചെയ്യുന്നത്. Okay, now 0 setting is done, and also the instrument is in the left face. Now unclamp the upper clamping screw, rotate the telescope and sight to the ranging rod at C. Okay, now you will get the point bisected. Clamp the upper clamping screw. For fine adjustments, you can use the upper tangent screw. Suppose you get the reading as obtained above. Okay, 90 degree, like the value you got in the previous video, so you note it down. So that is your horizontal angle. Now you have to repeat it 3 times. So next step will be you have to loosen the lower clamp, turn the telescope and sight to B again, and tighten the lower clamp. For fine adjustments, you can use the lower clamping screw, lower tangent screw. Now next procedure is unclamp the upper clamping screw, turn the telescope and sight to the ranging rod at C. Clamp the upper clamping screw. For fine adjustments, you can use the upper tangent screw. Again, note down the reading. So earlier ഇപ്പോൾ 100 degree എന്ന് കിട്ടിയെങ്കിൽ ഇപ്പോൾ ഇവിടെ 200 degree എന്ന് കിട്ടും. Okay, note it down. Again, loosen the lower clamping screw, turn the telescope and sight to the ranging rod at B. Clamp the lower clamping screw. For fine adjustments, you can use the lower tangent screw. Again, unclamp the upper clamping screw, turn the telescope and sight to the ranging rod at C. Clamp the upper clamping screw, and for fine adjustments you can use the upper tangent screw. So now this particular angle BAC has been measured 3 times. Okay, so sometimes if the first angle was 100 degree, you will get now the angle as 300 degree. So 300 divided by 3, that is the total angle divided by the number of repetitions. Number of repetitions in this case is 3. So 300 by 3, you will get one angle is 100 degree. Similarly, do this or repeat this procedure in right face left swing. So here in the first you have done it is left face right swing. Next you will be doing in right face left swing. So first transit the telescope, keep the vertical circle to the right of the observer, set 0, and using the set 0 and clamp the upper, okay, so that the reading won't change. Now loosen the lower clamping screw, sight to the, since you are going to do the in the opposite direction, so you have to sight to the rightmost point, that is C. Okay, so sight to C, clamp the lower clamping screw, and for fine adjustments you can use the lower tangent screw. Now unclamp the upper, turn the telescope towards B, sight B accurately, clamp the upper, and for fine adjustments you can use the upper tangent screw. Note down the reading. Loosen the lower clamping screw, loosen the upper clamping screw, lower clamping screw, turn the telescope and sight to C again, and clamp the lower. So the same reading will be shown here. Again you have to unclamp the upper, turn the telescope and sight to B, clamp the upper. For fine adjustments you can use the upper tangent screw. Note down the reading. Again loosen the lower, turn the telescope, sight to C, clamp the lower. For fine adjustments you can use the lower clamping screw. Unclamp the upper, turn the telescope and sight to B, clamp the upper. For fine adjustments you can use the upper tangent screw. Note down the reading. Now this is the third time, okay, we are measuring the same angle CAB. So divide it by number of repetitions. So here we have done it 3 times. So total angle divided by 3, you will get the angle CAB. So in the left face right swing, we have measured the angle BAC 3 times. Divided by the number of repetitions, you will get the angle BAC. In the left swing, that is in the right face left swing, we have taken the reading CAB 3 times and divided it with 3, and we got the angle. That is how you got the included angle CAB. Next step is using a measuring tape, measure the distance AB and AC. Now you can calculate the distance BC using the cosine rule. That is BC square is equal to AC square plus AB square minus 2AB AC cos of the angle alpha. Now this angle alpha should be the average of the value obtained from left face right swing and right face left swing. So this is the procedure. So all of you substitute the value of alpha which we have obtained in this example. ഒരു എന്താണ് ഹൊറിസോണ്ടൽ ആംഗിൾ മെഷർമെൻറ്റിൻ്റെ ഒരു വീഡിയോ കാണിച്ചല്ലോ. അപ്പോൾ അതിനകത്ത് ഒരു ആംഗിൾ നമുക്ക് കിട്ടിയല്ലോ. ആ ആംഗിൾ ആൽഫ ആയിട്ട് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുക. എ ബി ഡിസ്റ്റൻസ് 7.81 എ സി ഡിസ്റ്റൻസ് 9.545. ഈ രണ്ട് വാല്യൂ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് നിങ്ങൾ BC കണ്ടുപിടിക്കുക. So this is your experiment. Okay. ഇതിൻ്റെ അകത്ത് ഒബ്സർവേഷൻ കോളം അതുപോലെ തന്നെ പ്രൊസീജിയർ വാട്ട് ടു റൈറ്റ് എന്നുള്ളത് I have given in the group. Okay, I have shared that in the group. അപ്പോൾ പ്രൊസീജിയറും ഒബ്സർവേഷൻ കോളം അതുപോലെ തന്നെ സാമ്പിൾ കാൽക്കുലേഷൻ ഇക്വേഷൻസ് അങ്ങനെയുള്ള കാര്യങ്ങളെല്ലാം വാട്സപ്പ് ഗ്രൂപ്പിൽ നമ്മൾ ഷെയർ ചെയ്തിട്ടുണ്ട്. ഓക്കെ, സോ ദിസ് ഇസ് ദി എക്സ്പെരിമെൻറ്റ്. അപ്പോൾ നമുക്ക് ഈ വീക്ക് തൊട്ട് സിൻസ് വി ആർ ഹാവിങ് അല്ലെങ്കിൽ സിൻസ് ദി ഓൺലൈൻ ക്ലാസ്സസ് ആർ extended to next week also, lab online ആയിട്ട് തന്നെ എടുക്കാനായിട്ടാണ് കിട്ടിയിട്ടുള്ള ഇൻഫർമേഷൻ. സോ യു ഹാവ് ടു completely watch this video and you have to calculate the value of horizontal distance, and that is your class work for today. Okay. Once again, I repeat, the angle and the distances I have mentioned in this video. You have to note it down and do the calculation. And write down the procedure given in shared in your group, and also draw the tabular column, draw the rough sketch, and enter all the values. Okay, enter the values so that see ഇപ്പോൾ ഇതിനകത്ത് ഇപ്പോൾ 100 ഡിഗ്രി ആണെങ്കിൽ അതിനെ തന്നെ 3 times റിപ്പീറ്റ് ചെയ്ത് എഴുതിയാൽ മതി. യു ഡോണ്ട് നീഡ് ടു write it 3 times. Okay, അപ്പോൾ then okay, so I think you will be able to do and calculate and find out the distance BC by method of repetition. Okay, thank you.